All right, given that cubic equation, what I want you to do, I want you to do these first three. We'll do number 4 together. We'll do the graph and calculator part together. Evaluate f at -1, okay, the value of the function at -1. Find f at -2. And then using those points and what you know about a cubic function, sketch the graph. Okay, by hand. Put some nice points on there. And like I said, I'll give you a couple of minutes to do that. Do the first 3, and like I said, we'll do number 4 together on the graph and calculator. All right, let's take a look. See what you came up with. What'd you get when you put f? What is the value of f at -1? Should be 1. Yep, you're finding the value of the function when x equals -1. So if you plug that in, you should get 1. There's 1 point on the graph. You plugged in -1, you got 1 out as an answer. Therefore, -1, 1 is your first ordered pair. Okay? So if I go to -1, 1, I can put a point there. I know that's on this cubic function. How about f at -2? Should be -3. Okay, good. There's another point I can put on the graph. Now, before I sketch this is one of the concepts we're going to talk about in today's lesson. Remember that all polynomial functions are continuous. What that means is a nice smooth curve. They're not like piecewise functions where they might skip from one to the other. They're all nice and connected and smooth and continuous. Which means, by the way, if I'm going from f of -2 down here at -3, and then I'm going over here, what must happen somewhere between those 2 points on the graph? What has to happen if you're going from a negative y value to a positive y value? It's got to cross the x-axis. You got to have somewhere in between there. You're going from a negative to a positive. And again, it's continuous, so we know it's connected. So it's got to cross. There's got to be an x-intercept somewhere in there. Keep that in mind. We're going to talk about that coming up. But that's one of the reasons why I say that. Now when I say graph this by hand, now we're just going to use the knowledge that we have from the equation. Okay? There is one other quick point we could add. Anybody tell me what it is?
0.
The y-intercept. When x equals 0, y equals 1. So we could add the y-intercept very quickly without having to do really any additional math. Okay? And then we look at the fact that we have a positive cubic function, which means the graph is going to look something like this. Okay? Something along those lines. It's got the general shape of a cubic function, and it's a positive x cubed, so that's got that general increase as you work from left to right. Okay? Those are two kind of the main ideas for today of degree, value of a, what does that tell you about the graph? And like I said, what I'm really wondering here is I know that it had to cross the x-axis right there. There's an x-intercept there. And that's where the graphing calculator is going to come into play, okay? So as we move through this chapter, I told you we're going to get more specific. We're going to eventually not use the graphing calculator. You remember, again, I said before, remember about synthetic division? Eventually, we'll go through and we'll start using synthetic division to kind of work our way through it. But in order to do synthetic division, you have to start with a zero, with one of the zeros. That's where the graphing calculator is going to come into play. You're going to start with you're going to find the zero on the graph and then use it to do synthetic division and work your way from there. Okay, that's where we're headed. So let me at least show you how we find a zero. It's very similar to finding maximums and minimums. Okay, so let me switch over. If we go to the graphing calculator, and in your y equals, you put the function x cubed plus x squared plus 1.
If you store a number as x and you use x in there, will they put x as that number?
Yeah.
How do you undo
You could let me look at it. Let me look at it, because you could reset it. You could just go back and store like 0. You could store it as 0, so it's not an actual number. What's that? For now, don't worry about it. You'll be okay. For now, it'll be all right. So as you go through and you take a look at this equation, okay? If we go to the graph, we hit the graph button. There it is. That's pretty accurate to what we sketched in, right? It's got that same general shape. Notice it does cross the x-axis between -1 and -2. So there's the shape of the graph. Reminder again, if your graph looks something different than this, you can always go back to the standard graph. You can hit zoom at the top, and then number 6 is Z standard. It'll go back to your standard 10 by 10 graph. Okay. Now, if I want to calculate that value, because right now you don't have any other tools to find it, you're gonna go back into the calculate menu like you did with maximums and minimums. So you're gonna hit second and the trace button, and it'll take you back to this menu again. Okay, second and trace. And instead of finding a minimum or a maximum, now we're going to use number 2. We're going to find a 0. So if you hit number 2, it's the same concept with one difference. They're going to ask you to do a left bound and a right bound again. But now you're bounding the 0. You're not bounding the maximum or the minimum anymore. So when they say left bound, you're going to take your cursor and go to the left of the 0. Okay, so I'm going to go over to the left a couple of times and then hit enter. Then it asks you to put in a right bound. So move the cursor so you're somewhere to the right of the 0. And if you can notice, now the 2 arrows come up saying that the 0 is somewhere between those 2. And it is. So now whenever they say guess, the only thing you really have to worry about, just make sure the cursor is somewhere between those 2. Okay? So I'm going to arrow back just a couple of times. I hit enter, and there's my 0. It's not very nice, okay? But it's approximately negative 1.47. There's the 0 of our cubic function. Okay? Like I said, eventually we'll find ones that will be nicer than this, and we'll use them to do synthetic division, and we'll get to that. But this is the process to get the zeros that we're going to use. Okay? Let me go back to the lesson here for a second. So that x-intercept that we just found, that value is approximately negative 1.47. Okay? There's your x-intercept using the graphing calculator. Again, somebody had asked before class about if we use the graphing calculators like we just did in class, then why can't you use them on the test? And here's the difference, okay? What we just did, we would give you that on the test, so you don't need them. Okay, that's why. If you need a 0 to start off doing synthetic division later on, we'll give you the 0. Okay, that's why you don't need the graphing calculator. Plus, obviously, whenever you've got a graphing calculator in your hand, there's ways to kind of cheat the system of not really knowing what you're doing and letting the graphing calculator do it. So we'll give you what you need off of the graphing calculator and then not let you cheat the system. That's the reasoning behind it. Okay? So here's the first part of where we're headed. Here's the big overview. What we are generally talking about today are polynomials of higher degree, and we actually kind of already talked about a lot of the parts. We're just going to formalize them a little bit now. So cubic functions, quartic functions, things like that. Like I said, this is starting section 2.2 now. So now, here's what I was telling you before. The intermediate value theorem. I'm going to show you what it is. I would not write down the actual definition of it because it's one of those math definitions that's very confusing and wordy and symbols everywhere. I'll explain how we're going to use it to help us. That's what I'll tell you to write down. Okay? So here's what we're talking about. Don't write this down. You have two real numbers. If you've got two values of x, and here I use a and b, okay? On the graph that we just did in the warm-up, we use -2 and -1, okay? So if you've got two values where the corresponding y values are not equal to each other, what that means is in between those two values of x, over the interval, in this case, on the warm-up, we use the interval from -2 to -1. What that means is the function, because it's continuous, every y value between those has to happen. Let me go back. What I'm getting at is this. When you look at this graph, we said right down here at -2, -3. Then we said -1, 1. Notice the graph is continuous, therefore it hits every single y value between -3 and +1. That's what the intermediate value theorem tells us. How we are going to use it is just like we just did. We're going to use it to help locate zeros. That's the part I would go through and write down. Okay? We're trying to figure out where does the function go from positive to negative. Because if it goes from positive to negative, somewhere it must have been 0. Meaning you must have an x-intercept in there somewhere. That's the purpose that we're going to use the intermediate value theorem for. To help us locate zeros. If I were to give you a function and a table of values, you should be able to look at that table and say, oh, this y value was positive, that y value is negative. Therefore, somewhere between here, we must have an x-intercept. That's what we're getting at. Okay? We're trying to find x-intercepts. So as we work on these cubic functions, these quartic functions, things like that, this will at least guide us and narrow things down. It'll kind of focus our attention a little bit. That's how this helps. See a few people still writing. I'll wait for you. All right. So when we actually start taking a look at the graphs, the nice part about this year compared to last year with Algebra 2 is last year when we started talking about cubic functions, quartic functions, you probably hadn't dealt with that at all previously, or not very much at least. Now you at least know what the general shape of a cubic function looks like. You know about a quartic function, and now we're just revisiting those, okay? So the simplest form of any power function, x squared, x cubed, x to the 4th power, x to the 5th power, those are kind of your parent functions. The main thing you need to know is that even degree functions all kind of act the same way. They have a lot of the same characteristics, and so do odd degree functions. Okay. What I'm getting at, even though they have different shapes, some of the similarities, if you look over on the side wall over here, notice I've got polynomial odd degree, polynomial even degree. There's two posters over there. What I want you to notice is, so the odd degree one, that's a cubic function. Notice, where does it start? If we're working from left to right, where does that graph start? Up high or down low? Down low, right? Where does it end? Up high. The same thing would happen with a 5th degree function. Starts in one spot, ends in the opposite. Same thing would happen with a 7th degree function. Any odd function, the end behavior is what we're talking about. They're in two different spots. Okay? And we'll talk about end behavior in a second. Notice even degree. What do you notice about the end behavior for the even degree? Where are both parts of the graph going? Up. Okay, think about a parabola. That's a fourth degree function. Think about a parabola that's opening. They're both going up. So second degree, fourth degree, sixth degree. The end behavior for those go to the same spot. Think about a parabola that opens down. They both go down to negative infinity. Same thing with that. That W, if we have a negative in front, would turn into an M. And therefore, both parts of the graph go down. Okay? That's what I mean when I say that they're similar to each other. All right. So then let's talk a little bit about end behavior. We just did it. We just kind of talked about it. But end behavior is basically where does the graph start? Where does the graph end? Do they start and end in the same spot? Okay, both positive infinity, both negative infinity, or is start low, end high, or start high, end low? Okay, what happens? And what we're going to take a look at is this. Two parts, and we already did it on the cubic function of the warm-up. What's called the leading coefficient test, otherwise known as the A value. Is A positive or is A negative? And what effect does that have on the graph? That's called the leading coefficient test. And then the second thing we're going to look at is the degree of the function. If it's a quadratic, you know that it's going to be a parabola. If it's a cubic, it's got that S-shaped curve. If it's fourth. By the way, what are your options for fourth degree? What's the shapes? A fourth degree, yeah. Yeah, if it opens up, it kind of looks like a W. If it opens down, it looks like an M. Okay? So the degree and the A value will kind of determine what the graph looks like. That's what that says. That's what we're getting at. This next part, you don't need to write this down. I don't want you to take the time to write this down. I just want you to see the notation that we are then going to use in examples. Okay? Here's what the notation is going to look like. Okay? It looks messy to begin with. So one option, I might say if x goes to infinity, or as x goes to infinity, what part of the graph am I talking about? The left side or the right side? If x is going to infinity. Yeah. Think about the x-axis as a number line. If x is going to infinity, we're going to the right. I'm saying, all right, as x goes to the right, what's happening to y? Is it going up or is it going down? If it's going up, then we would say y goes to infinity. Just like that odd degree poster over there, the polynomial odd degree. As x is going to infinity, the y value is going up. Y is going to positive infinity. And like I said, I've got some examples for you. If x is going to positive infinity, but the graph is going down, then that means y is going to negative infinity. Okay? And then your other options, when we say x is going to negative infinity, we're just talking about the left side of the graph. It's called end behavior because we're looking at the two ends. Where does the graph start? Where does the graph end? Okay? That's what we're looking at. All right, let me give you some examples so you can see what we're going to do. It's easier than it looks. It is. It's easier than it looks. You'll see. Trust me. You got to trust me. I know I do say that a lot. One more thing, too. Okay? Just watch. Watch how easy this is going to be. First question. What's the general here? Whenever you're trying to determine end behavior, think of the general shape first. Then write the end behavior to match. What's the general shape of this function? It's cubic, right? And it's a positive x cubed. So the general shape of this graph is going to look something like that. Which means if you can picture that in your head, you can now write the end behavior to fit that. So as x goes to negative infinity. Okay. If we're saying x is going to negative infinity, we're saying as we go to the left, where are the y values going? Up or down? Down to negative infinity. So as x goes to negative infinity, y is going down to negative infinity. That basically says the graph starts low. Okay? Then we go to the other end. As x goes to positive infinity, where are the y values going? As x goes to the right, the y values are going up, which means the graph ends high at positive infinity. That's all that's saying. That's all we're looking at for end behavior. Okay, that's why I said it's easier than that last slide makes it look. Okay? As we go to the left, y goes down. As we go to the right, y goes up. Okay? Starts low, ends high. Let me give you another one. Same thing again. Let's start with the general shape of the graph. What's it going to look like? Fourth degree, so it's got either that W or M shape to it. Because it's a negative A value, it's opening down. You know what? In general, it's going to look something like that. Okay? Some sort of M type of shape. And again, as we go through the chapter, we'll start to get more specific. Okay? For now, we're looking at a little bit more general. All right, let's write the end behavior. I put both of these because where are both parts of the graph going? Take a look at the arrows. Starts low, it's going to negative infinity on the left, and it ends low, going to negative infinity on the right. Okay? So both of the y values are going to negative infinity, which is always what happens with even degree functions. Both the start and the end always go to the same place. Either both positive infinity or both negative infinity. Okay. How we doing? Making sense? Okay. Preston, how we doing? Easier than when I was telling you? Gosh darn it. There we go. Got it. Okay, let's try one more here. This is the first part of your assignment today is quite literally matching. Okay? You're gonna have some graphs and some equations and say match them up, tell me which ones go with which. Notice I've only got 4 equations, but I've got 5 graphs, so one of them is going to get left out. Okay? Number 1.
B.
Why B?
Because it's positive.
Because that's the right answer. Because it's a 4th degree, so we know it's a W or an M. It's positive, so we know it's opening up. There's B right there. All right. So B is done. Let me get that out of there. All right. How about number 2? A? Why not C? Because C is both A and C are cubic functions.
Because it's negative.
Negative A value. They call it the leading coefficient test. If A is negative, that means there's a general decrease. There's your general decrease to the graph versus increase. So your answer here is A. Very good. Okay, that one's done. How about number 3?
D.
Why D? How do you know it's D? Okay, if you take a look, and I don't know if your Algebra 2 teacher talked about this last year or not. I did in my classes. Okay, I don't know if everybody did. Here's another reason why in the last chapter we talked about increasing versus decreasing behavior. We've got a 5th degree. This graph is starting by increasing, right? Then all of a sudden it switches for a little bit and decreases. Then all of a sudden it switches and increases a little bit again. Then it goes back and decreases again. Then all of a sudden it goes back up again. How many different directions did we go in? Oh, look at that. Five different directions, 5th degree. Okay? Well, change of directions. Okay? So that part of it also comes, think about it like a parabola, x squared, right? Part of the parabola is going up, part of the parabola goes down. 2 different directions, x squared. Same thing with a cubic function. Goes up, comes back down, goes back up. 3 different directions, 3rd power. That doesn't always work, okay, just as a heads up. But most of the time, I would say 95% of the time that works, okay? That's a made up percent, by the way. But that's most of the time it works. Last one, how about number 4?
E.
Yeah, that one's E. You got a parabola opening down, that's the only one we have. Okay? So there's end behavior, there's the idea. We're going to go a little bit more specific today where we're just going to talk about a couple of examples of let's use the end behavior, but then also let's find a couple of zeros of things you already know how to do. Okay? So we're going to go a little more specific. Not a lot. First question on this one, what's the graph look like? Parabola opening down. And we've talked about the last couple of days, I could find the vertex, I could do all of that. I'm not going to today, okay? I'm going to find the zeros and then sketch it off of that, okay? So, if we're finding the zeros, that means we need to set this equal to 0. How do I solve that? You can factor. Could I do it in a different way? You could just solve. and take the square root, because there's only one x here. So you could solve it. Okay? Theoretically, you could do quadratic formula. It's a whole lot of extra work, but you have multiple options. Somebody in one of the previous classes said, and I'm going to go the factoring route only because of the fact that that's kind of where we're headed, is we're going to be factoring more often in this chapter. So somebody said, I want to factor it, but I don't really like that negative x squared. Can I multiply or divide everything by a negative 1?
Yes.
As long as it's an equation, you can.
Yeah.
Okay? So as long as you can keep things balanced, you can do it. So I'm going to multiply everything by a negative 1 and change the signs, which means that negative x squared will become positive. That 49 will become negative. And that 0 will still be 0. Okay? Now, we can either solve, add the 49 over and take the square root, or factor, because this is a difference of squares. Again, I'm going to go the factoring route, only because, like I said, that's what's coming. You're going to be factoring more often. If I factor this, it ends up being x plus 7 and x minus 7, which means, what are my zeros?
7 and negative 7.
Yep, 7 and negative 7. Okay? So now we can put that on the graph. Here's negative 7. There's positive 7. We said this is a parabola that's opening down, and we can just sketch it from there. There's at least a general, somewhat accurate sketch of this parabola. Like I said, we could find the vertex. You know how to do that. We've talked about that. I'm not going to worry about it today, because today we're kind of focusing on the zeros. Let me give you another one, a little bit different. I got 2 examples left. Just kind of different versions of the same type of stuff. What is it? This one's a parabola opening up. Once again, I could go through an opposite of b over 2a. I could find the vertex, plug it back in. We could do everything we've talked about. Right now, let's factor. Let's go through and set this equal. And it is what, Preston? Yeah, this is a perfect square. If you factor this, we get x plus 5. X plus 5 when we factor. Which means, what's the 0?
Negative 5.
X equals negative 5. But because of the fact that I had 2 of the same factors, what does that mean about that 0?
It just touches the...
It's a double root, which means it just touches the x-axis at that point. Okay? Remember, if you have a single root, like we did up above here, that means it's going through the x-axis. If it's a double root, that means it's just touching the x-axis at that point. So in this case, if I come over here to negative 5, and I know that that's a 0, we already said it's a parabola opening up.
When it's only squared.
There's what it looks like in general. Turns out, that's the vertex. If it just touches, because it's a double root, that means it's touching and bouncing off of the x-axis at that point. Okay. One last example. What shape? 4th degree means it's either a W or an M type. Positive x to the 4th, so this is going to be a W. Okay. So now, let's find some of the values so that we can add some actual points to the graph. So same thing again. I'm going to set this equal to 0. What's step number 1? Pull out an x squared. When we're trying to factor, greatest common factor is always the first thing. Let's pull an x squared out, which means we're left with x squared minus x minus 20. And now the stuff that's in parentheses is a whole lot easier to factor. Okay? Which means zeros. X equals negative 4. There's one of your zeros. X equals positive 5. There's a second 0. Here's something on the very first chapter P test that a lot of people forgot about when you were solving equations like this. Whatever you pull out, greatest common factor is still a 0. Okay? So it's not just those. This also gives you x equals 0. But what do we know about x equals 0?
It's a double root.
Because it came from x squared. It's a double root. Fourth power, remember we should have 4 zeros, right? There's 1, there's 2, and this one's a double root for the third and the fourth one. So if we put that on the graph, -4, +5, we put points at all 3 of those. Hi there. Oh, yep, come on in. I'll be right with you.
Sure.
So as we go through and we take a look, okay, we said we know this is a W opening up. There's some zeros. And we said 0 is a double root. So your graph looks something like this. Single roots, it goes through the x-axis. Double root, it bounces off of the x-axis. Okay? So you know it just touches and then goes from there. Okay? How we doing? Remember doing most, if not all of this last year? All right. Here's your assignment for today. It's a little bit longer, but the 1 through 8. The 1 through 8 is just matching. Here's 8 graphs and 8 equations. Match them up. Okay? So it's still not too bad, hopefully.
15 through 30. That's like
Can you handle 7 or 8 problems in pre-calculus? I hope so. How many are we done? 57? Is that right? Okay. Yeah. So after that, once you've got the assignment, you guys can go. Have a good day.